How does thermal conductivity affect cooling system design? Imagine trying to keep a hot cup of coffee from cooling down too fast or a computer chip from overheating. The secret ingredient in both cases is how well heat moves through materials. That's where thermal conductivity comes into play. It's a property that tells us how easily heat can pass through a material, measured in watts per meter Kelvin. Think of it as how quickly heat can travel from one side of a material to the other. In designing cooling systems, especially for electronics or machinery, choosing the right materials is key. Materials with high thermal conductivity, like copper or aluminum, are often used because they transfer heat rapidly. Copper has a thermal conductivity around 400 watts per meter Kelvin, making it excellent for heat sinks and cold plates. Aluminum is also popular because it's lighter and costs less, with a thermal conductivity of about 200 watts per meter Kelvin. These materials help spread heat evenly and prevent hot spots that can damage components. Fourier's law of heat conduction explains how heat moves through materials. It states that the heat transfer rate depends on the thermal conductivity, the area through which heat flows, the temperature difference, and the thickness of the material. If you increase the thermal conductivity or the surface area, heat moves faster. Making the material thinner also helps. So in practical terms, a thin, wide cold plate made of copper will transfer heat more efficiently than a thick, narrow one. Designers use this knowledge to optimize cooling systems. For example, they select high conductivity materials to reduce thermal resistance, which is the obstacle to heat flow. They also design the shape and thickness of cooling components to maximize heat transfer. Thinner cold plates with larger surface areas are common because they conduct heat quickly and allow more contact with the cooling medium. The interface between the heat source and the cooling element is also important. Using thermal interface materials like thermal grease or pads helps fill gaps and improve contact, reducing thermal contact resistance. This step is crucial because even the best high-conductivity material won't perform well if there are gaps or uneven surfaces. In liquid cooling systems, the cold plate's material affects how well heat is transferred to the coolant. The coolant then carries the heat away through convection. The better the conduction through the cold plate, the more efficient the entire system becomes. For high-power electronics or rugged environments, high thermal conductivity materials keep temperatures safe and stable. For insulation or heat retention, low thermal conductivity materials are used instead. Understanding how thermal conductivity influences heat transfer helps engineers design more effective cooling solutions. It guides material choices, shapes, and sizes of cooling components, ensuring devices stay within safe temperature limits. Whether using air, liquid, or advanced cooling methods, knowing this property helps create systems that work reliably and last longer. In essence, thermal conductivity is a fundamental factor that shapes every aspect of cooling system design, making sure heat moves away quickly and efficiently.